are all in Lisbon, but hopefully next year. All right, so I'm going to speak about a number of things that probably overlap with two of the topics of the workshop. 2 out of 3 is probably not so bad. All right, so here are my collaborators that did almost all of the work. I'm only the spokesperson here. Good. What's the motivation? So the motivation comes from 2 sides. On one hand, in quantum field theory over the past number of years, new tools have been developed to compute physical observables in some supersymmetric QFTs in various number of dimensions. And these are presumably exact tools to compute the path integral in the presence of some sources. Okay, so this is a tool that we usually don't have in strongly coupled quantum field theory. So it's a good idea to understand it and to use it as much as we can so that we understand quantum field theory. On the other hand, this same tool can be viewed through the lens of ADS-CFT, where it's well known that the path integral of a certain class of QFTs that admit holographic duals is the same as the path integral of the full string or M theory with certain boundary conditions. So in many cases, this has been used in this way, where you use some kind of an effective flow energy supergravity approximation of the string or M theory to learn about the strongly coupled QFT. But you can also try to push it the other way around. If you have a new tool to compute the path integral in the QFT, you can try to learn about string or M theory, which is a bit more ambitious. More specifically, we will anchor ourselves again in the standard large N limit, but we'll try to go beyond the usual supergravity approximation. So we'll try to see how much we can push this left-hand side here to learn about the right-hand side. And there's at least 2 reasons to learn about the right-hand side. One reason is if you're a string theorist, you may have learned that it's hard to quantize string theory in general Ramon backgrounds, especially when the vacuum is ADS and you have non-trivial fluxes. So things are not easy on the string theory side, and very little is known. More generally, you might be interested in black holes and their thermodynamics and their physics in general. And so presumably this ADS-CFT duality should teach you something about black holes. And as we will see in this talk, we can learn a little bit about their thermodynamics. Quite a bit, actually. All right, so these are very lofty goals here. So I'm going to focus on some specific examples so that I can tell a story. There's been recent progress on some of these ideas in the context of 3D superconformal field theories with ADS4 duals in 11 dimensions. So this will be the topic of my talk, but many of the things I say can be extended to other number of dimensions, to type 2b or massive type 2a and so on. All right, so that's the motivation. And okay, we're a small crowd here, so you should really feel free to interrupt me at any point. I don't have to cover all my slides, so jump in whenever you feel like it. Okay. So here's my plan. First, I will use a relatively well-known example of ABJM theory on the round sphere to kind of set the stage and the notation, and also to illustrate the type of exact answers we can compute. Then I will move to kind of the new results that we obtained for a certain specific partition function that was already mentioned in Dario's talk. And then I will speak about how these QFT results apply or find implications in holography and black hole physics. And finally, I will mention other examples that are beyond this ABJM theory. Okay. If there are no questions, I will move on to ABJM on S3. Okay, so first of all, what is the ABJM theory? Very quickly, it's a 3-dimensional Chern-Simons matter theory. It has 2 gauge group, UN times UN. The Chern-Simons levels are equal and opposite, labeled by the the integer k. This ensures that the theory has parity. In addition, the theory has actually certain type of matter multiplets, bifundamental chiral superfields in n equals to 2 notation. Now the superpotential is given here, and if k is bigger than 2, the theory has n equals to 6 supersymmetry. For k equals 1 and 2, special things happen with the spectrum of local operators. There's these monopole operators that are light when k is 1 or 2, and you actually have an enhancement to n equals 8 supersymmetry. And so the claim to fame of this model is that it actually is the low energy theory, like the quantum field theory on the world volume of n and 2 branes, probing a certain orbifold of C4. I should note that this orbifold, if you think of C4 as a cone over S7, this orbifold is actually smooth, so it's a completely smooth manifold, the base of the cone. Okay, so there are kind of two interesting limits at large n. So you can take n large, the rank of the gauge group, and keep k fixed, and then this will correspond to a limit in which you are actually describing M theory on ADS4 times S7 mod zk. And as I said, this is a smooth action. Okay, and the mapping of the parameters, well, we have two-dimensional full quantities in 11 dimensions, the 11-dimensional Planck scale and the scale of ADS, big L, and they're related to k and n in this way. I'm skipping over here factors of 2 and pi, just giving you a flavor of how things are scaled. There's another interesting limit. So strictly speaking, I don't have a continuous coupling in the ABJM theory because k is quantized, it's a Chern-Simons level, but I can also scale k with n, and when both of these integers are large, there's an effective, almost continuous coupling lambda that looks a lot like the Hopf coupling of a usual large n expansion in an ordinary gauge theory. And so this is the limit in which you are effectively, you have reduced from 11 dimensions to type 2a, and the dual is ADS4 times CP3. So S7 can be thought of as a U1 bundle over CP3, and you're effectively, as you increase k, you're making the circle very small, and you're going to the type 2a limit. Okay, so I'm going to be interested in both of these limits. Okay, and now, of course, in type 2a, I have another scale, the string scale, and so this is how it's related to G string and k and lambda. All right, so that's a lightning overview. The ABJM theory, in the absence of any sources, is a conformal theory. I can put it on Euclidean R3, and that is conformal to Euclidean S3. And so this tool, this conformal map allows me to go smoothly to S3 without actually modifying the theory. And now on S3, I can use the powerful tool of supersymmetric localization, which often requires compact Euclidean manifolds so that the path integral converges. And then these people, following ideas of Witten, Nekrasov, Pestun, and others, they computed this path integral. So this integral that you see here, this ordinary integral, is equivalent to the path integral of the full quantum field theory. And this answer here is valid for any value of n and k. Okay, these mu and nu you should be thinking of as complex numbers, parameterizing the, roughly speaking, the scalars in the vector multiplets, so something like Coulomb branch parameters, and this integrand comes out of the detailed analysis of the localization calculation. Okay, so what you have to do is you have to compute these integrals and then find out the partition function. At large n, though, well, obviously, if n is equal to 1,000, you have to compute 2,000 integrals. That's going to be hard, and the integrand is not particularly simple. However, at large n, we have new tools to analyze such integrals, such matrix models as they're called, and there's various ideas have been explored. smart people have recognized these integrals as related to known models arising from the topological string. Other people have just studied this at large n and fixed k numerically by a saddle point approximation. Yet another approach has been to reorganize the integrand and then observe that it reduces to a Fermi gas, so fermions without interaction, but with some exotic kinetic terms, which is in some sense integrable. Anyway, these are the methods that have been used to attack this kind of integrals at large n. And the answer that emerges is really beautiful. So at large n and fixed k, which I'll call the M-theory limit, the partition function looks like this. So there's some exponentially suppressed terms at large n. Let me call them instantons. So these presumably arise from some non-perturbative effects in M-theory. And then the whole 1 over n series resums in a nice way into this Airy function with some prefactors. Okay? So the Airy function is a well-known function in mathematical physics. Here it appears with some strange arguments. B and C are some rational numbers here that are related to the Chern-Simons level. So you see that the argument of the Airy function is not n, it's some shifted version of n. And we'll see this appearing over and over again. This annoying prefactor is order 1 in the large n limit. It purely depends on k. It can be written in this integral form or in a series expansion at large k. So essentially, you know explicitly the full 1 over n expansion resummed. And what you're missing are these instantons. Okay. When I say instantons, there's really no instantons here, but non-perturbative effects. Okay. And you can really go into the books and study the Airy function and expand this at large n, and there's a systematic way to expand to any order that you want. And you get explicit large n expansion of this form. This, by the way, in the early days of these investigations, answered the famous question, how can you get an n to the 3/2 scaling of the free energy if you have a theory of n by n matrices, right? If you are a high school student and I give you an n by n matrix, you should say that it has n squared degrees of freedom in it. So something special happens in M theory such that you'll get n to the 3/2 here. And this is understood from this matrix model. All right, so that's a well-known story. What we observed is that you can actually play with the expansion of the Airy function and reorganize it as an expansion of fixed n over k, something that a priori you don't have the mathematical right to do. So I'm only looking at this perturbative part here, resummed, and then re-expanding it in a new way, and then resumming again, but now organizing the expansion as if I'm doing string theory. And these f with 0, 1, 2, 3, 4, and so on should be the string theory. This flat G should be the type 2 string free energy of genus G. And you can really resum at any genus that you want. You can write down explicit expressions. So what I'm missing here are both e to the minus square root of n corrections, as well as e to the minus square root of lambda corrections. So I'm missing worldsheet instantons and D2 brane instantons. Another thing to note here is that these simple free energies of the string are expressed not in terms of lambda, but in terms of lambda hat, some shifted version of lambda. Okay, good. So by the way, this is a new trick that we used, and these results were, some of them were explicitly known in the literature, including the e to the minus square root of lambda corrections, but we kind of found a much easier way to find them. And actually in the literature, if you go to higher enough genus, people couldn't do it, and we have a simple way of obtaining it, the final answer. Okay, from the point of view of ADS CFT, all of this is a wealth of information that you should be trying to recover from the 11-dimensional bulk view. So how does this work, and what can you actually do in practice? So here I've done this expansion again in the M theory limit. So we're back to fixed K large N, and I've kept only the first three terms. The reason is that these are the terms that are most leading at large n, but also these are the terms that we know how to account for in the bulk. Okay, so how does this work? The leading term, the n to the 3/2, is by the usual ADS CFT dictionary, is related to the on-shell action of the ADS4 times x7 solution. Here, in our case, x7 is simply this quotient of the sphere. I can compute the volume very easily. And so ADS CFT informs me that this on-shell action here on the right-hand side should be the same as the free energy. And indeed, if you put in the numbers, you recover the field theory answer, the leading term. The sub-leading terms are more subtle. They have to do with higher derivative terms in M theory. Those are notoriously hard to study. What we did in this work is to study the problem in 4 dimensions. So again, go to some 4D gauge supergravity theory of the type that Dario had in his talk, and then in it study higher derivative terms, and then carefully fix the coefficients, and then you can account for this and n to the 1/2 term. And the log n, this 1/4, was understood in a beautiful paper by these people, where they essentially treated the full tower of KK modes on ADS4 S7, and they treated every mode as a quantum field on a fixed background and computed the one loop partition function. And when you do that, there's a log n. And when you resum the KK modes, you get infinity. But if you regulate the sum, you get 1/4. So that's like a half-a-minute explanation of what these people did. So this log is coming not from an on-shell action, it's coming from a quantum loops of the KK modes. Okay, and this is essentially all that is known from the bulk, modulo a paper that I'm not sure I understand all details of, but anyway, it's a paper in the literature where people claim, these people here, they claim that they can find the full Airy function, the all-ordered thing, by doing supersymmetric localization in 4-dimensional supergravity. I'm not going to say much more about this, but anyway, there's a paper out that claims that they can recover all the dots. Well, it's not an 11-dimensional paper, so it doesn't give you any insight of how M theory produces the dots, but it's some idea how to recover the dots. Okay, good. All of this was computing a number. So if you fix K and N, you're really computing. Yeah.
Hi.
Yes.
Can you go back to, I'm going to ask a question that you don't want me to ask about this paper that claims things. So can you remind me which theory do they consider in 4 dimensions?
Yeah, there's many things to say about this paper. So they consider 4D, well, what they should do and what they don't do is that they should study 4-dimensional n equals 8 supergravity with all its fields, and then all the KK tower. They don't do that. They study 4-dimensional n equals to 2 gravity, and somehow argue that the rest of the fields don't contribute, and then they have to fix some measure, and they fix it by hand to get, anyway.
So the starting point is already kind of a
is already questionable,
unjustified truncation. Yes. Let's say, yeah, among us, and then I remember that there are some assumptions about which mode fluctuates and which don't, which wasn't very clear.
Exactly. Okay. So they freeze certain things, they ignore KK mode. Anyway.
Yeah, it's very difficult to see how this has to do with M theory.
Exactly. It could be. I mean, it could be that everything from M theory that you have ignored is just Q exact, right? But you have to show that it is, right? That's Anyway, we can talk about it later.
Okay.
Okay. So this was computing a number where we should be better than this. We should be computing more than numbers. We should be computing functions. So functions will come from adding sources. So in QFT, of course, it's very natural to add a source to the path integral, differentiate with respect to it, and get endpoint functions. You can try to do that here, of course, because of supersymmetry, you should be adding only special sources that are compatible with the supercharge that you have in your SUSY localization. And there are these 4 parameters that I know about, 3 masses, M1, M2, and M3, and a squashing of the sphere that keeps U1 times U1 invariance. So they're very special sources, but in the presence of those sources, we conjecture this expression here for the path integral. So I say conjecture, in some limits, this has been actually rigorously derived, but the full answer hasn't been rigorously derived, but it obeys certain non-trivial consistency conditions. We can talk about it later. The point is that there is this Airy function keeps on controlling the behavior at large n, even in the presence of sources, and then you have to modify the parameters that appear in the Airy function in a certain way. What is this good for? What is this good for? One thing that it's good for is that this object, the path integral on S3 in the presence of sources, actually encodes in a not so obvious way, but it encodes integrated endpoint functions of the theory, of the conformal theory on flat space. So it might be exotic to study path integrals on S3. This is not something that you look and find in West and Bagger or in Peskin and Schroeder, but I claim that these are useful objects precisely because of the connection to the theory in flat space. Holographically, these things encode endpoint functions of the graviton in ADS, which can be used to constrain or compute corrections to the string and M theory. And this is really a big thing that you can study, and I don't have the time to explain how it's done, but I think it's an important thing to keep in mind, that these answers that we find from the QFT are computing for you string theory information in non-trivial backgrounds. Okay, all these lofty words can be made very specific in a simple example. So I use the sphere, turn off the masses, but only turn on this squashing deformation. And I claim from the formula above that I have an exact expression up to exponentially suppressed terms of the free energy. Then, very generally, you can prove a word identity here. So this first equality that I'm circling around has nothing to do with localization, nothing to do with large n, and so on. This is purely based on supersymmetry. A derivative of this free energy with respect to B, with respect to the squashing, derivatives is related to the 2-point function of the energy momentum tensor. And that's very easy to understand. This squashing sources the metric couples to the energy momentum tensor. So 2 derivatives with respect to the squashing pull down 2 energy momentum tensors. You have to work a little bit to find the precise relation, but it has been worked out and it's right here. And what I claim now is that if I know F to all orders, I know CT to all orders. So this is an illustration of what I meant here. CT is a property of the conformal theory in flat space. It's here, this is the 2-point function of ABJM on R3. And I've computed the only number, the only quantity that I don't know in this strongly coupled QFT. And you can do this for the 3-point functions and so on. So there's a whole industry here of computing such observables. All right, good. Once you know all of this, you should be asking, can I do it again for other manifolds? Maybe I'll find some interesting examples of other compact manifolds where I could exactly compute the partition function. I lost track of time, so can you tell me how much time I have?
You have about 36 minutes.
Okay, good. We have enough time to get going. Okay, so we found one example where we can make some progress. Okay, this may not be the first partition function that you want to compute from the QFT side, but I claim it's an interesting object for various reasons. So let me try to explain what it is. It's called the topologically twisted index. It's a long name, but it's relatively simple to understand what it is. So you put a 3D n equals to 2 CFT on this manifold, S1 times a Riemann surface. So the Riemann surface, I'm assuming it's smooth, compact, genus G. So these are not the spindles that we've heard from Dario about. This is an ordinary manifold. And to preserve supersymmetry, only on this Riemann surface, you do Witten's twist. So you use the R symmetry U1 gauge field of the CFT, you turn it on such that you cancel the spin connection. And then as a result, your supercharges are ordinary fermions on S1 and scalars on sigma, and you keep 2 real supercharges in general. And so this now is a compact manifold with certain background field for the R symmetry, and you can ask what is the path integral. It's important to emphasize that this QFT, although I've done a partial twist only on the Riemann surface, it's not a topological theory. So it has interesting correlation functions. And the reason it's called an index is because of this S1. It has an interpretation as counting certain BPS objects in the theory. These people in a series of papers have shown how to compute this path integral, how to write down this path integral as a matrix integral, okay, using SUSY localization. The formula looks a little bit scary, but the details are not important. What I want to explain a little bit is, so this N and K are our usual friends from the sphere. This delta is very much like the real masses that we saw before. So these delta 1 to 4 are related to the global symmetries of the ABJM theory. They have to sum up to 2, and this is a condition for supersymmetry. These funny ends are background fluxes for the background for the U1 global symmetries of the model. I have U1 to the 4th global symmetry here, and I can turn all of them on, but if I want supersymmetry, I need to obey a condition here. So these are the parameters in red. They're fully external, if you wish, sources that you're free to pick as long as you obey the constraints here before. And everything else is something that you have to sum over. This sum is over the magnetic fluxes of the 2 gauge fields of the theory on the Riemann surface. And then, or do integrals. So these integrals over x and x tilde are very much the same as the integrals that I had to do on S3. I have to integrate over the scalars in the vector multiplet of the theory. Okay, and then the integrand is this big mess. Okay, I'm not explaining how it's obtained, but this is the full answer. So now, so we have reduced the path integral of a QFT to this ordinary but super messy integral. So we've made some progress, but we still have to solve this integral. And well, you can try various ideas. I think the smart idea, or at least the one that we've used, is to use the Cauchy theorem. So I have this integral over these complex variables, and then I have to specify a certain contour. And okay, once you have an integral like this, you can look for the poles and the residues and try to express your integral as a sum over those poles and residues. And this is what can be done. So this first line here is a rewriting of that integral using the Cauchy theorem. But the problem is, so now the x and x tilde, although I use the same notation, they're really the location, if you wish, the location of the poles. But to find them, to find the x and the x tilde that I have to use in the first formula here in the first line, I have to solve complicated algebraic equations. So I've traded a complicated contour integral for a complicated system of algebraic equations using the Cauchy theorem. And these algebraic equations, I guess, for the authors of these papers, they looked a lot like Bethe-Ansatz equations. And so they call them Bethe-Ansatz equations. I'm not aware of any standard integrable system that these are the Bethe-Ansatz equations of, but this is how they're called in the literature. Anyway, we can think of them as certain involved algebraic equations. Okay, so the problem we have to solve now is to solve these equations at large n and see what happens. You can use a saddle point approximation, and this has been done in this paper. The tools are relatively standard. The details are annoying and not so standard, but essentially you go to large N, you think of these x and x tilde as an eigenvalue of a matrix, and then approximate that with an eigenvalue distribution, and then essentially write down a classical action for this eigenvalue density, find the saddle point, and try to solve for that eigenvalue density. And this has been done to leading order at large N, and this is how these eigenvalue densities look like. Good. So this, if you wish, is an analytic approach. It has been shown to work only to give you the leading n to the 3/2 behavior of the index. Okay, so this is good for something, but it's good only for the, as far as I know, for the leading order. So what we did is we said, okay, we tried to extend this to subleading orders at large N. Analytically, we didn't find a way, probably because we're not smart enough. But we then said, okay, we'll write a piece of code that will fix n to be, let's say, 1,000 or 500. And then ask Mathematica, solve these complicated algebraic equations. I will now have, 2 times n of them to solve. And I will, because they're very, very complicated, they have many roots. But at infinite n, I know the correct solution is this one. So at finite but large n, I will ask Mathematica to find me the nearest root. Okay, so it is not exactly that as a solution, but it's as close as you can get. And then I do this for many, many values of n, thousands and thousands, and I try to see how the answers look like. And they look beautifully simple, so beautifully simple that we can actually write down the full answer. So this is an analytic formula that we obtain from the numerics. So it's very hard to imagine how we can get there, but I think we were able to do it simply because the answer is so nice, and there must be a reason it's so nice, but I don't know that reason. Anyway, I claim that the final answer fits on one line. So it's not an array function, it's a simpler function. It has n to the 3/2, n to the 1/2, log n, and then a finite piece. It has 4 pieces. The thing that is very subtle here is that this is not this n that appears in the formula is a shifted version of the original n. So n is the number of M2 branes, or the rank of the gauge group, and I have to shift it in a very specific way that depends on these parameters delta. Yes, please, Dario.
Yeah. Sorry, I didn't want to interrupt the sentence. But anyway, so is there an expression for this x and x tilde that you can make us imagine, or I don't know?
Yeah,
I don't want to write it; it's difficult. But is there like a finite expression that depends on n?
Good. So that's a very good question. Can I reverse engineer also the solution for x and x tilde?
Yeah.
We haven't tried very hard. We focused on the final. In a sense, this x and x tilde are some kind of intermediate calculational tools that I don't have a physical way to think about, right? It's some crutch to solve those integrals. So we didn't spend a lot of time in trying to analyze this, but indeed it may be a good point to go back and revisit this, because this may allow us to analytically solve the problem.
But sorry, I'm confused. Aren't x and x tilde the solutions to the Bethe-Ansatz equations?
Yes.
So you have not solved the Bethe. What have you done?
Good. So I have solved for if I fix n to be 500, I can tell you x and x tilde as numbers. So fix n, fix delta and k, give me those quantities, and then we have a code that will give you the x's. But then to compute the index, I need to solve these algebraic equations here in the middle, and then put in the x's back in the first line.
Right. And it's only when you put them back that you have this nice formula.
So,
well, at least that's what you have to.
This we have focused on guessing analytic expressions for the first line, because that's the physical observable. The x and x tilde is kind of intermediate step. but you're absolutely right that if you would like to approach this analytically, you
Yeah.
have to find a way to analytically solve these.
Yeah, if you can guess the axis, that probably it's a good step. Yeah.
Anyway, I cannot at the moment tell you the answer for the axis, but I can tell you the answer for the physical observable, the index, and it fits on this line. Okay.
Nice.
And as you see,
can I actually ask a question?
Sure.
You had this initially. You had this approximate result at large n, given in terms of the area function, and that had an argument which was something like n minus k divided by 24 plus something.
Yeah.
So how does this argument, your new n hat, compare with the previous one?
Very good question. So the k over 24 is the same. Let me remind you. Maybe even earlier. You see, the minus k over 24 is the same. But this extra piece, well, first of all, here I'm not turning on the deltas. But even if you turn on the deltas, then B changes. You see, again, the k over 24 is robust. But this extra piece is not on S3 and on S1 times the Riemann surface differs. Okay, so one of the big open questions is what M theory or string theory effect is responsible for these shifts of n? We have ideas, but let me get to them in the conclusions. At the moment, I don't have a good answer. But the shift is not the same. The shift is morally the same. There's a k over 24 and then a 1 over k piece with some coefficient, but the coefficient changes when I change from S3 to S1 times the Riemann surface.
Okay.
Yes, good. So we have this big answer. It has many parameters. It has these magnetic fluxes n. It has these real masses delta. It looks like a bit, well, it's on one hand simple, but on the other hand, it has too many parameters. A simple limit, which we have a good reason to take in the QFT. So I call this the universal index for various reasons, but basically tuning the parameters to these values corresponds to the minimal twist that you can do for the ABJM theory. So when you put the ABJM theory on this S1 times Riemann surface, you must switch on an R-symmetry gauge field, as was explained also by Dario. So that is a must, and everything else is an option. Everything else is what Dario called mesonic twists and so on. These flavor symmetries are additional things that you can or cannot switch on, up to you. So this universal index is when all of these extra optional things are switched off. And then it takes a very simple form. And as you see here, so this is probably the object to be compared with the area function. And as you see, the shift is plus 2/3 instead of plus 1/3. I don't have a good answer why the coefficient changes. But anyway, in this case, we can actually really go into detail and study this order n to the 0 piece. This little function f hat is not a function of capital N. So it's some finite contribution. And then we were able to study it very accurately numerically and, well, guess some of the series expansion and so on. If you fix k, so this expansion here is for large k. If you are at small values of k, we can compute this to like 20 digits. So I give you here only like the first 8 or 9, but we can compute it to very high accuracy. Okay, so this f hat is the analog of this curly a that appeared in front of the area function, which was also not really known in closed form. Okay, good. So this is essentially, I claim these are analytic results that are obtained in a little bit of a funny way with many heavy and very precise numerics. And we have checked that they're accurate. They deviate from the exact answer by e to the minus square root of n corrections. And our numerics is so good that we can even fix the coefficient here in front of the square root of n and the coefficient in front of this exponent. So we can, making fits, really show that what we're missing are these exponential terms and estimate exactly the magnitude of those terms. Okay, so we can now also do this other game, other idea. Now I have an answer at fixed k large n. I can try to reorganize it at large n and large k with fixed ratio. And so these f's now, again, fg, these are the free energies of the type 2a string at genus flat G with certain boundary conditions. And they again take very nice, simple, finite expressions. But now the shift of lambda is exactly the same as it was on S3. So this lambda hat is exactly the same as what we had before. Again, I don't have a good understanding of the shift of lambda, but we observe that it's the same. And of course, if you're a string theorist, you should sit down, quantize type 2a strings on ADS4 CP3. And actually, it's not exactly ADS4. I will show you the background and tell me how to compute these genus G free energy of the string. I'm not holding my breath that this can be done soon, but hopefully smart people can find a way to do it. All right, what is this all good for from the perspective of ADS CFT? So everything I told you so far is basically large N quantum field theory. So I managed to resum the large N series and miss only exponentially suppressed terms. Why is this important? So there's a simple solution. So this obviously will have something to do with ADS, but let's see exactly what. I claim that the following solution is a supersymmetric Euclidean solution of 4-dimensional n equals to 2 supergravity. It was written down first by Romans and then studied by other people later on. So how it looks like, you have a circle parameterized by tau, you have the Riemann surface, and you have the extra direction, the radial, if you wish, of ADS. So this already looks like what I'm studying in the field theory. I have some explicit metric function u written here. G is 1 over the scale of ADS. So G is like 1 over L. There's a Maxwell field, F. The magnetic flux of the Maxwell field is completely fixed. It's not a parameter. It's fixed. Once you fix what is the Riemann surface, a sphere, a torus, or a hyperbolic one, you fix completely the flux. This is the supergravity analog of this twist that I have to do. And then the electric flux is completely free. So this capital Q is any real number. Okay. However, if you want a smooth solution, you'll get a lower bound on Q, on the magnitude of Q. The sign is arbitrary, but the magnitude has a lower bound. And then essentially what happens with the circle tau is that it collapses to 0 sides. So it looks like a cigar. So tau and R form a disk, and then the Riemann surface goes along for the ride. It's finite size. And at the cap-off point, I have to impose a certain periodicity of the tau circle to have a smooth solution. And this is what I find, that periodicity must be. Okay, so this is a family of Euclidean smooth solutions with 2 supercharges. In a special case, they can be interpreted as black holes. So if you choose a hyperbolic Riemann surface, so genus more than 1, and if you take Q going to 0, this solution is nothing but the extremal Reisner-Nordstrom black hole. The only somewhat exotic thing is that you should remember that in ADS, I don't have the usual Hawking theorems, so that the horizon can actually be any Riemann surface, not only a sphere. So these are smooth horizons, but they're hyperbolic. Okay, and then you can compute this on shell action. This is the regularized finite part, and observe the well-known fact that the entropy of the black hole is minus this on shell action. This was generally expected by Gibbons and Hawking and works out in detail in this example. Okay, so this is kind of an overview of this solution. And as I said, in this limit Q going to 0, it's nothing but the magnetic Reisner-Nordstrom in ADS, extremal. This can be uplifted to M theory. one way to do it is when the internal space is a sphere, S7, you take the metric I showed you above, you add a CP3, you add a U1, the fiber is specified by the Kähler, the potential for the Kähler form on CP3. So this looks a lot like what Dario was showing us. And then this A is the four-dimensional Maxwell field, now becomes a part of the metric. It's a Kaluza-Klein gauge field. And then there's certain four-form flux. Okay, so now I claim that these results I was showing you for the topologically twisted index amount to a prediction for the path integral of M theory on this background to all orders in 1 over n. So that's the big statement I'm trying to make. You may or may not believe it, but some aspects of the statement are certainly true because we have checked the first few terms. So again, I can focus on the most leading 3 terms of this expansion of the index. And the leading term, the n to the 3 half term in the index, is again matched with the on-shell action of the black hole. The sub-leading n to the 1 half term is again captured by these 4 derivative 4-dimensional supergravity corrections. And again, the log n can be mapped to 1 loop contributions from the KK modes on this background. So in some sense, well, in a very specific sense, we know how to compute these 3 coefficients independently from the field theory and from the bulk. So this is a confirmation of the big statement I was making here that, well, presumably the full series should have some M theory origin, which is still to be understood. As I said, this can be viewed also as an all-order prediction for the entropy of the black hole. Good. Now, I've been focusing so far on this limit of delta equals 1/2. So these real masses are very finely tuned, essentially to 0. And then I have also tuning the magnetic fluxes for the flavor signatures. But of course, you can start switching these things on in the QFT side. And what they correspond to in the bulk are additional scalar fields, Z and Z tilde, and additional Maxwell fields, AI. So the solutions that you should be looking at in the bulk are much more complicated. We call them black saddles because in general, they're not Lorentzian black holes. They're Euclidean solutions, supersymmetric in a certain 4-dimensional n equals to supergravity. And we showed how to construct them explicitly. And the leading order n to the 3/2 on-shell action agrees with the index I showed you. Subleading terms are harder to compute. In some cases, we have arguments why they should match. But anyway, at this point, the only thing that has been matched from the bulk is the leading order for all values of the parameters. And of course, the expectation is that this index that I showed you will be the full path integral to all orders in n. And again, I want to emphasize that there's some of the solutions here have an interpretation as a black hole of the type that Dario was mentioning, however, without a rotation. So these are static black holes with ADS2 times Riemann surface horizons. And then for general deltas and n to obtain the entropy is not simply the on-shell action. You have to do this Legendre transform and extremization that we heard from Dario. All right. Do I have 5 minutes or I'm over time?
Yeah, sure.
Okay, good. So this is basically the story for the ABJM theory. And I've tried to explain it both from the field theory perspective and from the bulk. We can do much more. We can do other models. We focused on holographic models in M theory. But I strongly believe that none of what I'm saying is very specific to M theory. If you find some massive 2A example or type 2B, it can probably be studied in a very similar way. Anyway, to explain what we have done, actually, here is some details. So we look first at another 3D n equals to 4 CFT. It's slightly different from ABJM. It's a Yang-Mills theory. So when you write down the Lagrangian, it's not conformal. It's a UN Young-Mills, so it's like n equals 4 Young-Mills in 3 dimensions. But then you add one adjoint and NF hypers, and there's no Chern-Simons term. So this thing undergoes an RG flow, and the claim is that in the IR, you'll hit a strongly coupled CFT. The bulk dual of this model is some specific orbifold of S7. I'm not explaining how we know this, but this is in the literature from 15 years ago. Well, 14 years ago. Anyway, there's a specific orbifold of S7, which is now different. The orbifold acts only on 2 of the complex coordinates. So I think of S7 as I put a cone over it, I get R8. I'm thinking of R8 as C4, and then I'm orbifolding Z1 to Z4 in this way. Okay, so this orbifold now has fixed points. So that's how it's different from the previous case. Long story short, we can essentially repeat the calculation. So now the matrix model changes, but changes in some known way. I'm ignoring all the details. So I have to do new integrals, new Bethe ansatz equations, new solutions, and so on. And what we find is, again, a finite simple answer for this index. So now I'm only giving you the index in the absence of these real masses. So this is what I call the universal index. And again, I have some, so I have 4 terms, n to the 3/2, n to the 1/2, log n, and a finite piece. And the n here that appears is a shifted version of n. And again, the shift depends on the rank of the orbifold in a certain way. And again, for all of these things, I can give you a black hole in M theory, and the leading order term at least matches the entropy. And we've also computed the subleading order term, but the log n has not been computed from the bulk. And this story keeps on giving, okay? So now you can go back to your list of holographic CFTs with ADS4 duals in M theory. I went to my list, and these are the entries that I found. And for each entry, there's some specific description of the CFT. I use that in the localization formula. I find the Bethe ansatz equations. I solve them numerically. I solve them many, many times. I make linear fits and so on, and I find these simple answers. All of these are, of course, up to exponentially suppressed terms. And for all of these 4 models, you don't need to know what they are, but in every case, I have explicit bulk duals with explicitly known metric and fluxes. And there's a black hole, this magnetic Reisner-Nostrom black hole can be embedded in those ADS4 backgrounds. So this wealth of information here again about the path integral of M theory on these backgrounds, I claim. All right,
Nikolay?
Yes, please.
Before you conclude, so let me ask you this question. First of all, is this published or it's not?
Yeah. So we put out a 4-page paper where we announced the results basically. And we're writing now 2 papers. One is about ABJM with all the details, and one is about all these other models. Okay. So there should be 2 papers, but as you said, the summer break.
Okay. Yeah, the summer break. But okay. So the leading order terms, those multiplying n to the 3/2, as we all know, they are proportional to 1 over the square root of the volume of the internal thing. Yeah. So that they have a geometric interpretation. Now I can see the logarithm always appears with a factor of 1/2. So that seems to be completely universal. But the intermediate terms, those to the with the n to the half, they have numbers which depend on the model, Yep. So the question here is, well, that would be my guess, but would you have a guess for what they correspond to in the geometry?
Oh yeah,
okay, you know the answer.
Well, you ask me whether I have a guess. I always have a guess. Okay. But whether I do know, so I can give you a very strong argument why the n to the 1, not n hat to the 1/2, but n to the 1/2 piece comes from higher derivative terms. Okay. Now, the way that for ABJM, so this term here, n to the 1/2 term, we are able to compute it in this paper by doing 4 derivative supergravity in 4 dimensions. In general, this type of terms should come from M theory higher derivative terms, which come at order 8 derivatives. And actually, we've been heavily searching the literature. All of these terms are not known. So even if I wanted to do the reduction, I don't have a starting point, simply because, well, we don't know all 8 derivative terms in M theory. The ones that have been used for asymptotically flat black holes are basically the geometric ones, because for Calabi-Yau reductions or whatever, Ricci flat manifolds, internal ones, the flux vanishes. But here, I always have some kind of a Sasaki-Einstein or Einstein manifold or something like this, and I always have curvature and internal fluxes and so on. And then it's very hard to explicitly compute it. So the full piece, I don't know how to compute. We made some progress of computing, like if you wish, one of the 2 pieces. You see, it always comes with a k over something and then 1 over k.
Yeah.
So one of these 2, we made progress unpublished, how to compute it from 11 dimensions using one of these 11-dimensional terms.
Yeah. So the guess here, it's that instead of being volumes, there'll be some other geometric invariants of just purely of the geometry, such as, I don't know, some Pontryagin classes or something like that.
It is not, unfortunately, at the moment, I think it's not so simple as to be a topological invariant. It's something much more metric dependent. It's like some integral of r to the 4th, Riemann to the 4th. It's not a topological invariant, it seems. But let me not make a strong statement.
Okay.
Yeah. Or maybe it's a topological invariant I don't know about. That's also a possibility. It certainly, the flux is important here, right? Because the solution in 11 dimension looks like this, right? So I have this A as a part of the manifold, and I have this internal flux also. And that appears when you do on the reduction from 11 dimensions. So it's not a purely like a Gauss-Bonnet type term or whatever. Yeah, but certainly the general answer is that these n to the 1/2 terms depend on the geometry of the internal space, which is also obvious here because as I change the model, the details slightly change of the coefficients and the shifts and so on. The 1/2 is universal. It will be super nice to understand why it's such a universal thing. Why is the spectrum of KK modes? Somehow the full spectrum should not be an important thing, because the full spectrum is going to be different from all these models, but the 1/2 is always the same. So there should be some universal aspect of the KK modes and their one loop partition functions that will always give you 1/2 log n, but I don't know how. Okay, anyway, I think I'm out of time basically, so let me wrap up. I told you about some results which I called exact, but they are not exact because I'm missing exponentially small terms, but almost exact, of the partition function of ABJM theory on S3 and S1 times the Riemann surface. I told you how these connect to results in string and M theory in ADS CFT. This, in the context of this index, leads to a prediction for the entropy of extremal ADS4 magnetic black holes. And I showed you that all of this is not really specific to ABJM. It's valid for at least 5 or 6 other models that we studied. And I think it will be valid much more generally. Okay, what's the homework? Well, as I said, you can try to do it for other CFTs. We have some in mind. Of course, we should not forget that the results are nice and we've done a lot of checks, but still nothing beats an analytic derivation. So we should work on that. There's other manifolds on which you can study the partition function. So I've emphasized only 2 types, but there's other ones. This is quite interesting. Why are these shifts in n and shifts in lambda appearing with these specific coefficients in the context of the Airy function? Bergman, Hirano accounted for some piece of the shift by observing that charge quantization in M theory is modified by the presence of 8 derivative terms. So a piece of the shift must be due to the fact that what you call N, the relation between the 4-form flux in M theory and N is slightly modified by a constant. But this shift in the charge is not accounting for the full shift. Okay, and we're trying to understand this also with my friends. And okay, we need, I think, we have to go back to the drawing board and try to understand higher derivative terms in the string and M theory with non-trivial internal manifolds that are, what I mean is things that have flux and that are not Ricci flat. Well, the final one is my dream. In asymptotically flat black holes, there is the OSV conjecture, which is a deep statement about relation between black hole entropy and a topological string. The results here, a lot of them smell the same way, but I certainly don't have a concrete, deep statement analogous to BCOV or OSV. That's all I have to say. Thanks.